In cities across southern China this past summer, temperatures reached over 40 degrees Celsius. That's more than 104 degrees Fahrenheit. Concrete buildings absorbed the heat like ovens. Asphalt roads became almost impossible to walk on. And yet, in several neighborhoods, residents reported that they turned off their air conditioners entirely. Not because they were saving money, but because they simply didn't need them anymore. Behind this, Chinese researchers have quietly unlocked technologies that Western media has almost completely missed. Buildings that cool themselves without electricity. Materials that reflect solar heat while radiating away infrared energy at temperatures below the surrounding air. And urban systems that turn entire city districts into naturally cool zones. This is not a demonstration. This is being deployed at scale, right now. To understand why this matters, look at global energy consumption. According to data compiled by the International Energy Agency in 2024, buildings account for approximately 40% of the world's total energy use. Of that, cooling and heating consume the largest share. In hot regions, air conditioning alone can account for over 50% of a building's electricity bill during summer months. And the problem is getting worse. Heat waves in 2023 and 2024 killed more people globally than at any other point in recorded history. The World Health Organization estimated that heat-related deaths increased by 68% between 2000 and 2020. In cities like Delhi, Karachi, Phoenix, and Shanghai, extreme heat is now a public health emergency. The typical response has been more air conditioners. But this creates a devastating cycle. Air conditioners pump heat outside, which raises outdoor temperatures. Higher outdoor temperatures require more air conditioning. More air conditioning burns more electricity. More electricity means more carbon emissions. More emissions accelerate climate change. And climate change produces more heat waves. Chinese scientists decided to break this cycle from a completely different direction. Instead of cooling air, they would cool buildings themselves, using nothing but physics. The first breakthrough came from researchers at Southeast University in Nanjing, China. The team spent years developing what they call cooling cement, a modified concrete material that maintains temperatures up to 26 degrees Celsius cooler than conventional cement in direct sunlight. That is almost 47 degrees Fahrenheit of temperature difference between traditional and cooling concrete when both are exposed to identical sunlight conditions. The material was announced in January 2026 and immediately drew global attention. According to their published research, buildings constructed with cooling cement showed dramatic reductions in indoor temperatures. In test buildings in Nanjing, interior temperatures during peak summer days stayed 8 to 12 degrees Celsius lower than adjacent buildings using standard cement. That is 14 to 22 degrees Fahrenheit cooler indoors, using no electricity, no fans, and no air conditioning. The cooling cement works through two combined mechanisms. First, its surface reflects a much higher percentage of incoming solar radiation than standard cement. Second, it actively emits thermal radiation in a specific wavelength range where the atmosphere is transparent. This means the heat travels through the sky directly into space, rather than warming the surrounding air. The result is a material that literally sends heat away from Earth. The physics behind this is called radiative cooling. It has been theoretically understood for decades, but making practical materials that could achieve significant cooling has been one of the most difficult challenges in materials science. Traditional white paint or reflective roofs work well during the day, but at night, they lose their advantage, and they cannot cool a surface below the ambient air temperature. Radiative cooling materials can do something more remarkable. Because they emit heat in wavelengths between 8 and 13 micrometers, a range where Earth's atmosphere is essentially transparent, the emitted energy travels through the skies and escapes to space. Since space itself has an effective temperature near absolute zero, This creates a heat sink of essentially infinite capacity. Chinese researchers have engineered surface structures at the nanometer scale that selectively emit in this atmospheric window while blocking heat absorption. The result is materials that can cool below ambient air temperature, even in direct sunlight. In laboratory tests published across multiple peer-reviewed papers between 2023 and 2025, these materials achieved surface temperatures 5 to 16 degrees Celsius below the surrounding air. This is exactly what makes the Southeast University cooling cement so significant. It brings this laboratory-only technology into construction-scale production. But cooling cement is only the beginning. In July 2025, a separate team of Chinese researchers announced an even more radical breakthrough. Led by researcher Yangzhe Hou, the team developed a biodegradable cooling film they call BPCM. This film can be applied to any surface, a car roof, an outdoor umbrella, a hospital tent, and it will reduce that surface's temperature by up to 2 degrees Celsius. That is 16.5 degrees Fahrenheit of temperature reduction from a thin, flexible film. What makes this material unique is what it's made from. Most radiative cooling materials developed in Western laboratories are based on petrochemical plastics or ceramics. These raise long-term sustainability concerns. Some contain forever chemicals, others cannot be recycled. The BPCM material is completely different. It is made from polylactic acid, or PLA, a plant-derived biopolymer that biodegrades naturally in soil within months. According to their study published in a major scientific journal in July 2025, the material can be welded together using only water to create large planks. There are no petrochemical solvents, no industrial adhesives. Water bonds it. Yangzhe Hou described the discovery as a breakthrough in sustainable materials engineering that could help combat rising global temperatures and hotter cities. The team is now exploring large-scale manufacturing methods. Applications extend far beyond buildings, cooling for farm equipment, cars, and even wound dressings in hospitals. In 2024, a related breakthrough appeared in the journal Science, one of the most prestigious scientific publications in the world. A Chinese research team demonstrated a radiative cooling material capable of reducing building temperatures by up to 16 degrees Celsius. That is nearly 29 degrees Fahrenheit of cooling, achieved without a single watt of electricity. The material was announced in a paper picked up by Xinhua and the South China Morning Post. What makes this discovery notable is not just the cooling capacity, but the scalability. Unlike laboratory curiosities that work on tiny samples but fail at larger sizes, this material has been produced in strips large enough to cover roof surfaces. In one demonstration reported by SCMP in November 2024, a Chinese-American research team, in collaboration with an American university, developed an advanced emitter that could reduce building energy demand while simultaneously mitigating urban heat island effects. The lead researcher stated that radiative cooling technology has been demonstrated as a passive, energy-free cooling method with significant potential to combat climate change. In 2025, KPMG Advisory China published a detailed industry report on passive radiative cooling. According to that report, the technology is now transitioning from scientific exploration to engineering deployment across multiple Chinese provinces. Investment is rising, government policy is favorable, and end-user demand is growing rapidly. The industry that most people have never heard of is quietly becoming one of the fastest-growing sectors in Chinese materials science. While researchers worked on materials, Chinese cities have been rolling out something else entirely: outdoor cooling systems that operate at neighborhood scale. Videos began going viral on Chinese social media in the summer of 2025, then spread internationally. They showed residential apartment blocks in Guangzhou, Chongqing, and other southern cities releasing fine clouds of mist during heat waves. Some Western viewers called it the outdoor AC, Despite the name, these systems are not air conditioners in the conventional sense. They use high-pressure mist cooling based on the physics of evaporative cooling. Nozzles installed on building exteriors, streetlights, and public squares release water droplets so small they evaporate almost instantly. The evaporation absorbs heat from the surrounding air, reducing outdoor temperatures by 5 to 8 degrees Celsius within seconds. The energy requirement is minimal, just enough to pump water at high pressure. According to reports by Parametric Architecture and Chinese state media, these systems are now installed across dozens of Chinese cities. Some are permanent infrastructure integrated into building design. Others are mobile units deployed during heat waves. In Guangzhou alone, the municipal government reports that these systems reduced heat-related emergency room visits by approximately 30% during the summer of 2025. Whether this is truly a scalable solution or a partial fix remains debated among urban planners. But it represents something Western cities have not attempted at this scale. Radiative cooling and mist systems address surface heat. But China is also pursuing a much larger urban strategy, one that reshapes entire cities. It is called the Sponge City Program. Launched by the Chinese Ministry of Housing and Urban-Rural Development in 2015, the program has now been implemented in over 30 major Chinese cities, including Shanghai, Wuhan, Xi'an, and Shenzhen. The core idea is deceptively simple. Traditional cities are designed to move water away as fast as possible. Concrete drains, sewers, and rain gutters channel rainwater into rivers and away from urban centers. Sponge cities do the opposite. They absorb, store, and slowly release rainwater across the city through permeable pavement, green roofs, urban wetlands, bioswales, and underground water storage. The cooling effect comes from multiple mechanisms. Green surfaces cool through evaporation. Stored water provides thermal mass that moderates temperature swings. Vegetation shades urban surfaces from direct sunlight. And microclimates around wetlands remain 2 to 4 degrees Celsius cooler than surrounding built areas. According to studies published by the Chinese Academy of Sciences in 2024, sponge city districts show measurable temperature reductions of 1.5 to 3 degrees Celsius during summer heat waves compared to conventional urban areas. That does not sound like much until you consider the scale. In a city of 10 million people, a 2-degree reduction translates to lower cooling costs, fewer heat-related deaths, and reduced strain on electrical grids across the entire population. Now let's talk about scale and consequences. According to KPMG Advisory China's June 2025 industry report, the Chinese passive radiative cooling market is projected to reach several billion US dollars in value by 2030. Chinese manufacturers are already exporting cooling materials to Southeast Asia, the Middle East, and parts of Africa. Government subsidies cover up to 30% of the cost of adopting passive cooling technology in new construction. Traditional air conditioning uses about 10% of all electricity generated on Earth. That number is projected to triple by 2050 as global temperatures rise and developing countries adopt air conditioning at scale. If Chinese-developed passive cooling technologies can replace even a portion of that demand, the impact on global energy systems would be enormous. There is also a geopolitical dimension. Materials, science, and construction technology are traditionally dominated by American, European, and Japanese firms. Chinese firms now hold leading positions in radiative cooling patents, biodegradable film production, and urban cooling infrastructure. According to patent tracking data compiled by the World Intellectual Property Organization, Chinese researchers filed over 60% of the world's radiative cooling material patents between 2020 and 2025. The gap continues to widen. American research institutions like MIT, Stanford, and Princeton have their own cooling programs. But the transition from laboratory to commercial deployment has been slower in the United States. This is a familiar pattern by now. The breakthrough physics may originate anywhere. The industrial scaling happens in China. The technology extends beyond urban centers. A study published in January 2026 by researchers examining rural Chinese housing showed dramatic results from combined passive cooling strategies. Rural self-constructed homes in China's cold, temperate regions were retrofitted with a combination of nighttime natural ventilation, envelope retrofitting, window shading, and adjusted window-to-wall ratios. The result was a 43% reduction in annual cooling demand and a 50% reduction in peak cooling loads. This was achieved without adding any active cooling equipment, just smarter design. In developing countries where air conditioning remains a luxury, these strategies could dramatically improve indoor climate control without requiring electrical grid expansion. Chinese firms are already exporting these technologies globally. Yangzhe Hou Chemical exports biodegradable cooling films to Southeast Asia. Cool Roof Solutions International, based in Shanghai, provides reflective coatings to construction projects in the Middle East. Chinese cement companies, including CNBM, are integrating cooling capabilities into their standard product lines. Compare this with the United States. American passive cooling research is genuinely world-class. Stanford's Professor Shanhui Fan and his team pioneered radiative cooling breakthroughs in the 2010s. Companies like SkyCool Systems have commercialized rooftop cooling panels, but the scale of American deployment remains small compared to China. There are no American cities systematically retrofitting entire neighborhoods with passive cooling infrastructure at the pace China is achieving. Looking ahead, the pace of change is accelerating. By 2027, Chinese researchers expect the first commercial-scale cooling cement production plants to be operational. Southeast University is partnering with major cement manufacturers to bring the material to market. Ready-to-use cooling paint, based on the same principles, is expected to be available for residential retrofits by 2028. The BPCM biodegradable film, developed by Yangzhe Hou's team, is projected to reach large-scale production by 2029. Cost estimates suggest it could be competitive with traditional building materials within 5 years of commercial launch. The Sponge City program continues to expand. By 2030, the Chinese government aims to have 80% of urban districts in participating cities meet Sponge City design standards. This will represent hundreds of billions of dollars in urban infrastructure investment. Passive cooling is likely to be integrated with other sustainability technologies. Combined with rooftop solar panels, green walls, and smart building management systems, entire buildings could soon operate with near-zero energy demand for climate control. This is not science fiction. This is happening now. The materials work. The infrastructure exists. The manufacturing base is scaling. The only question is how quickly the rest of the world adopts these technologies, and whether Chinese firms will dominate the global market by the time Western countries catch up. If this video gave you a clearer picture of how Chinese researchers are quietly rewriting the physics of urban climate control, hit subscribe to follow more research-driven analysis. The next video examines a different Chinese engineering achievement. Thanks for watching.